Try. All right. So hey everyone, like Robin said, I'm Greg. I'm from Toronto. I work at Instagram now, and I want to talk about sanitizing all the things. So I want to talk about some of the code analysis tools that we have available to us in Xcode. We've got like the static analyzer, the address sanitizer, thread sanitizer, the new undefined behavior sanitizer, and so on. So I want to focus on two of these today, the address sanitizer and the thread sanitizer. Let me start by asking, how many people have used one of those two before already? 2, 3, 4, 5, 6, 7, 10-ish or so. Okay, cool. So you can always open up your own project, you edit the scheme, and then you can enable these things. This is from the, not today's GM, but from the beta. So the main thread checker, I think, is relatively cheap, so that it's always on. But you can see the other options for address sanitizer, thread sanitizer, undefined behavior, and a whole bunch of other options like zombies and things like that if you've used them before. So on your own time, you can always open up your own projects, enable these, run them against your own code, see what they find. But what I want to do today is dig in a little bit and look at how they work and what kind of things they're going to find. So I'll draw a little bit of a parallel here to test-driven development. And there's the classic red-green refactor cycle. So you write a failing test, and then you write the code to get the test to pass, and then you refactor, rinse, and repeat. And maybe similarly, if you get a bug report, you're supposed to write a test that exercises the bug and fails, and then you fix it, and then you make sure the bug is fixed, and you make sure your test passes. So then it's like, well, why do you start with a failing test? And then the idea is you want to confirm that you've actually fixed it and have like a test case for it, and then you want to add it to the test suite so that in the future, you won't reintroduce the bug, you won't get a regression or something like that. So that's the kind of model I want to follow and bring it over to the sanitizer. So I want to know exactly what code, what kind of behavior is going to trigger the sanitizer. So I want to follow a similar pattern to TDD. So we'll write some code, try to get the sanitizer to trigger and give us a warning or an error or whatever it does. And then once we have that failure condition, we can sort of see what exactly triggered it and how can we fix it. So I think that's the best way to understand exactly what these tools are going to be doing for us. So I want to talk about two of them today, the address sanitizer and thread sanitizer, given these lovely acronyms that you'll sometimes see in the code, ASAN and TSAN. So I want to go over what each one does, why you might want to use it, and then we'll have a little, perhaps, interactive coding session, kind of like pair programming, but multiplied by 50 or something like that. So this is the agenda for what I want to cover for each of the sanitizers. I want to talk about what it is, the very important so what, why you should care and why you might want to use it, a little bit about how it works, and then we'll have a live coding demo. So I brought notes on paper because you never know when things will not work. So that's what we'll do for each one. So let's start with the address sanitizer. What does it do? So normally you allocate some memory, and then you're good. You've got your allocated buffer. There's an unallocated buffer after it. You've got a pointer or something, and you read the data, and you go ahead through the buffer, and you're good. But then, for whatever reason, your math is incorrect, and you go past the buffer, and then bad things happen. So that's the sort of failure case that you have. Swift is usually pretty good because it's typed, it knows the size of arrays and things like that. But there are ways around that as well. So that's the kind of case that the address sanitizer is going to look for. So why should you care? Buffer overflows, cause of many security vulnerabilities. You'll get like very subtle bugs where if you're running in debug mode, the unallocated memory might be 0, but then when you run it in release mode, it might have some garbage data or vice versa, and you get these very subtle bugs that show up sometimes, but not other times. And then if you have bad memory access, you can get crashes at runtime as well, so it's just all around bad stuff. So that's why you should say, yes, I want to sanitize my use of memory properly. So what's the strategy that we have here? The basic idea is to fence off the parts of memory and say this part of memory is properly allocated, this part isn't, and to be able to tell the difference at runtime. So that's the basic strategy that the address sanitizer is going to take. So you ask for some memory, you get your allocated buffer, that sounds good, and then it will also allocate a little bit of extra space before and after the buffer that you allocate. So you got a little bit of padding there. And the idea is, in most cases, when you allocate a buffer, then the overrun is going to be sort of before or after. It's probably not going to be like way, way down the line. It's going to be adjacent. So you get a little bit of padding there. And then that's the allocation. But then it's like, how do you know what part is allocated and what part isn't? So there's another concept called shadow memory. And it says, all right, I'm going to keep track. So I'm going to say that part in the middle is OK to use, but then that buffer that I allocated before and after, that part is what they call poisoned. So it's poisoned memory. So that's the basic idea there. The shadow memory, it looks like you're like doubling the size of your memory because you allocate that much space and you need to allocate that much space for shadow memory, but it's a little bit more compressed. It's about 1 byte of shadow memory per 8 bytes of buffer. So there is a memory hit. That's why running the address sanitizer is a little bit expensive because it has to do all these extra checks. You have to allocate the extra padding. You have to allocate space for shadow memory. I forget what the exact numbers are. It's something like a 2 to 5x increase in memory, something like that. So it's not something you want to run all the time, or you don't want to ship it to the App Store or something like that. So a little bit more about how it works. So every time you call malloc to allocate some memory, then it's going to actually call this address sanitizer version of malloc that allocates the shadow memory as well. It does the marking. It allocates the extra padding and that kind of thing. Every time you call free, it's also going to call the sanitizer version. So it's going to clean up the shadow buffer, mark it as unused or mark it as used, and then free the memory. The additional thing that it does is if you allocate some memory and then you free it, normally that memory could be allocated. The next time I allocate memory, it'll reuse that block. But with address sanitizer turned on, it will try not to reuse the memory. It'll say, I'm not going to reuse that. I'll give you this memory over here. So the idea is to keep the unallocated memory around and marked as poison so that if you access memory that you freed, it can sort of find it. So that also doesn't help with memory usage. So when you free the memory, it'll do this special routine. And then the expensive part is every time you access memory. So if you do pointer access, then it's actually going to wrap the call first. So if you say, I would like to access memory at this address, normally you just go to the RAM and you look at it. But with address sanitizer turned on, it first has to go to the shadow memory and say, is this valid? Is it poisoned? And it has to check every single time. So your application will run a lot slower because it has to do all this extra work every single time. All right, let's move on to live coding, the best part. So let's give it a try. Let's see. I need to turn on mirroring. And then I have a text editor. Let me just make sure the font is big enough. And I also have my command line. Make sure that's large enough. Cool. Let's give it a try. I'm going to, we'll start something in Swift. So we'll import foundation. Is that big enough? That is not big enough. How's that? Acceptable? Okay, I can't really tell. Let me just save this once so it gives me a nice file name. That's not the right folder. Okay, so we'll try our address sanitizer 1 or 0. We should start from 0. Here we go. It can be partly interactive here. How do we create a buffer and overrun it in Swift? If I do something like, var numbers equals like 1, 2, 3 or something like that. If I do this, then I should get a compile time error. So that doesn't really do it. I want to actually like trigger the address sanitizers to say, hey, you went past the end of memory. So how can we do that? Does anyone have any ideas? The unsafe mutable buffer pointer, you say. Yeah, that's a good one. So let's try that. So we've got our memory here. I'll make a pointer. So it's going to be an unsafe mutable buffer pointer. I forget exactly. Unsafe is always unsafe. Mutable means I can edit the data. Buffer, I believe, means it's going to be an array, I think is what it means. And pointer means pointer. So I'm going to initialize one of these to use that buffer, the numbers. And have to give it a count. So this is where I can do it. I can say the count is like 20 or something like that, right? And then let's loop over it. So I'll loop over the value. We'll use enumerate, which I know is not great. Is it enumerated? Like that? Yeah. And let's just print it out. So I'll say index. I'm sorry? Oh. Value, something like this. So let's give it a try. I'm going to compile it. Did I call it asan something? There we go. So compile it, I'll run it. And you can see my 1, 2, and 3 are here, and then it's got like garbage data for the rest of it. But it let me do it, and it didn't complain about it. So again, this is just the plain old file, so we're good. Let's compile it again, and I'll turn on the sanitizer. Is address like this. So again, if you're using Xcode, you just set that nice checkbox, but I'm just doing it on the command line just to be a little bit faster. So we'll turn on the address sanitizer, recompile it. I'll run it again. I don't think you can turn on the sanitizers in playgrounds now, because there's no scheme and there's no settings. I would have done the playground otherwise, yeah. And it just runs, so it doesn't actually do anything. So what's going on here? So this is still a mystery. Maybe I should file a radar. But I think the idea is here that at the access point, at this point here, as far as it knows, I've declared it to have a size of 20. So this loop going 20 times is actually valid, even though I'm going past the end of the array. So the address sanitizer doesn't actually pick this up. But what you have to do is allocate your memory and then go past the point. Here I've allocated the memory and I just have a pointer, so this actually won't pick it up. I don't know how many people actually use the unsafe pointers, so who knows, but if I duplicate the radar, I'll tweet it out and everybody can, if I file a radar, everybody can duplicate it. So instead, we'll find the Swift example eventually, but why don't we move to everyone's favorite language, C, instead? Because it's very easy to trigger in C. So I just want to do it once just so we can see sort of how it works, and then we can come back to Swift. How many people are writing C, Objective-C, C++? OK, so about half. I'll call it half. That's pretty good. So let's go ahead and look at that. So we'll include some libraries here. I think we need standard library. Let me just save this once so I get code highlighting. We'll declare a main. What do people do? Double star, or do they do it like this? How many people do it like this? And how many people, how many people do double star for their second argument? One person, OK. All right, so let's just do something really simple. I'll make a buffer of size 10, and then we'll do like buffer 20 is equal to 42 or something like that. Really simple. So we declared it size 10, 42. We're going past the end because we're accessing the 20th element, so this should give us an error, we hope. Let's compile it. Clang, what do I call it? 1. Like this. And you can see I actually get a compiler warning saying, wait a minute, index 20 is past the end of the array. So right away it's warning us. And then, so it's pretty good. It says you declared it as 10. I'll go ahead and run it anyway. And then I believe it will just run. OK. Let me turn on the sanitizer. Address, I think, like this. And then I'll run it. Nice stack buffer overflow. When I tried this earlier, it actually crashed. I got a segmentation fault error 11, and now it's actually running. So who knows? But that's the address sanitizer at work. It'll say you did this thing here at this place over here, and then it has one object, and so on. And you'll get this nice little memory map saying what the buffer was and how you overflowed it. So that's kind of how that works. OK. I'll skip over the second example. I was going to do one with malloc, but it's the same idea. You malloc 10 bytes, you go past the end, and then it will kind of go ahead. So when you run it without the sanitizer, it just runs. If I like printed this out or something like that, it would be totally fine. It would be like, again, like the Swift example. It'll print out the garbage numbers. But then when you run the sanitizer, then it gives you the extra warning. So why don't we do something similar to this, but we'll do it in Swift, and then we can see it triggered in Swift code. But I think that just goes to show that it's kind of difficult to trigger the unit tests for the address sanitizer in Clang in the C++ to see how they did it in Swift, and then that's kind of how I got the hint. So let's try it in Swift. So we'll import foundation, and we'll make a pointer, just like we did before, but this time I'm going to allocate it. So we'll do an unsafe mutable pointer of type int. We'll do an int 8, allocate capacity 10, let's say. So this will allocate enough space for 10 integers, 8-bit integers, so it'll allocate 10 bytes, basically. And then I can just say, let me just initialize it to 0, so it'll be all zeros, and then I can just do an unsafe access, like P20 or something like that, just like this. Let's give that a try. So no warning this time. And if I run it, it just runs. OK. Let me go back and try something. I'll print index 20 is, and we'll access it. So I've got a write, and then I've got a read. Let me recompile it. I'll run it again. And it says index 20 is 42. So again, if you had this code in there, you would just be like, oh, it works. I'm accessing the 20th byte, and I set it, and I read it, and it's exactly what I thought. Nothing is wrong. So, oops. I'm just trying to make it larger. All right, so that's good. Let's run it again, or let me compile it again, and I'll turn on the sanitizer again. So I just do sanitize this address, and I'll run it, and then you get the same kind of thing. So this time we get a heap buffer overflow. If I run it with debug, it'll give you a line number, things like that. And you can see here the wrap malloc. So it's not just regular malloc for the memory. It's actually doing the address sanitized version of the wrapper. And then it's in the main, it's in the start. You can see the shadow bytes around the buggy address. So you can see it was this one here and so on if you want to figure out how to read that. And it's given us the error there for a buffer overflow. So that's the idea behind it. So again, it can be hard to figure out bugs if you are writing Swift or you're writing C and you're allocating your own memory and sort of looking around in it. It doesn't crash the program this time, although again, in previous times when I've tried it out, it sometimes does crash the program, but in this case it doesn't. And so running the code with the sanitizer will help you find these kinds of things. Yeah, all right. There are a bunch of other cases that it will, so the question was whether you would run this all the time or only if you're using the unsafe pointer stuff. There could be other cases where you trigger it. This is the only one sort of reasonable one that I found in Swift, and so that's why I'm going with it. But there could be other cases. I would say it's worth running your app and trying it. If you have like third-party code that's C or Objective-C, like you might catch a bug in there as well. Day-to-day use, though, I would say Swift is designed to be a much safer language. So probably, if I had to pick, I would say go with the thread sanitizer, which is coming up, rather than the address sanitizer. But probably it doesn't hurt to run your app and try it out. I don't know if I'd do it like, you know, continuous build or anything like that running under this or anything like that. But yeah. What about Objective-C? That you should do it all the time because, you know, it's not so safe there, right? All right. That was address sanitizer. So just to summarize again, I wanted to cover what it does, why you should use it, and how it works. So what it does, it'll help you detect memory corruption and errors. Why you would want to use it, buffer overflows are, I think, still the #1 sort of security hole that people use. I don't know, again, how important that is for iOS applications, but just crashes in general are not a good thing either. So help you reduce the number of crashes. How it works, the TLDR, there's a custom version of malloc, custom version of free, and every pointer access, again, is wrapped in this extra checking code to look at shadow memory. So there's definitely a slowdown. I forget, again, the numbers. It's like 5 to 10x slowdown or something like that, and there's a memory hit. You can check the documentation as well to see where it's supported. Again, I've forgotten the exact details, but some of them only work on the simulator, some of them only work on device, some of them only work on the Mac, so you can check out the documentation. I have some links and stuff later on. Yeah.
You mentioned if you're using third-party code, does that apply to like precompiled binaries or frameworks that kind of thing?
So if you,
problems with, say, AV Foundation?
yeah, so if you, because there's so many bugs in AV Foundation, I know that. If you're, because you have to enable this in the scheme, it does have to recompile the app. If you look at the screenshot for the scheme, it says this requires a rebuild or something like that. So there's two components. There's a compiler component, and then there's a runtime component. So it does have to be code that you have the source for. So if you have a third-party pre-built framework, it won't work. But if you have like, you know, you drag in the Xcode project instead of using CocoaPods or something, then it will work if you have the source code for it. Yeah. All right, cool. Let's move on to the thread sanitizer. So what is the idea, the big idea here? What is it doing? So we have something similar. We've got a memory buffer, and then we're going to read from it from different threads at the same time, which is totally fine because it's just data reading from multiple threads, no problem. But then the problem comes in when you introduce writes to it. So if you write on it from one thread and you're reading on it from other threads, then there's the chance of a data race where you're like, it's uncertain what the order should be. Somebody's writing it to it at the same time as someone is reading to it, and you should synchronize access and that kind of thing. So this is the kind of thing that the thread sanitizer is going to try to find for you. So to cover again the 3 points of the so what, why should you care? So race conditions are generally a bad thing. And they're very subtle, difficult to reproduce. It's the kind of bug where your users will say, I tapped on this button and it didn't update the thing. And you try it, you tap the button and the label changes. You're like, it works for me, and you close the bug. So it's very, very subtle, difficult to reproduce, because you're running on the simulator, you're running on device, you have a debug build, someone has a release build, and the timing is slightly different. And you also run into the Heisenberg situation where when you run it in the debugger, of course it always works because you're introducing pauses in there, where if somebody is running the test flight build, they may run into the bug more often. So very, very difficult to track down. And thread mismatches in general are just a difficult problem, concurrency and all that, but something that's important to get right, because if we're in the multi-core world, whatever the iPhone 10 has, magic 6 cores and 4 high-efficiency ones, blah, blah, blah. So yeah.
Can you briefly explain what are race conditions?
What are race conditions? Sort of what I had on the previous slide. So if you have data, I'll just go to the previous slide because I like the animation. So you have incoming data coming in from the network, let's say, and you're doing a network operation to fetch some data. So you're doing it on the background thread because you're a good citizen. You don't want to block the main thread. So you do that over there, and then you have another thread over here that's waiting for the data, and then it dispatches to the main thread to actually update the label with some text, let's say. So when that's going to happen, like what if you read the text and then somebody writes it later, and then you write back to it, like they type something in a text field and you update it. So sort of the order of operations becomes a little unclear. And again, sometimes it will work, the write will happen, and then the read will happen, and you're good. But then other times, you'll read first, and then you'll write. And then the user will say, hey, the label didn't update when I hit the refresh button. What's going on? And you're like, well, I don't know, it works for me, right? Because you have a breakpoint, and the app has paused, and so it has time to do it in the correct order. So that's the idea behind one example of a race condition. There are more serious ones as well, like if you close a file, and then you still try to read it or something like that, or you free memory and then you try to access it, that kind of thing can be a little more serious and can lead to an actual crash. My example is a little sillier. It's just like the text is wrong, but that's the idea behind a race condition. Yeah.
Like a canonical example would be if you have two threads trying to write, right? They're like both writing sheep or something. You'll get like SEEH, SFSP, like both threads are trying to write at the same time. They're both trying to access the same resource, right? So it's important to remember that it's thread across the thread, right?
Imagine if like two people had two pens and they were writing in the same spot, and it's like you would get, like I noticed that you have like some words from one person, some words from another, and it would just mix itself up. All right, so that's the why you should care. And threading is just hard, GCD, NS operation, dispatching to the main thread correctly, callbacks, you never know what thread the callback is going to be on. It's just a difficult problem, and it's easy to get wrong. That was supposed to be my illustration of a gnarly system of threads and so on. So that's the problem that we're trying to prevent. It's a hard problem. So how is the thread sanitizer going to help us? So every time you access data, this is, again, very expensive because it has to keep track of all kinds of things. So every time you access memory, it's going to keep track of the thread ID. It's going to grab a timestamp. It's going to say, is this a read or is this a write? And it's going to keep track of what bytes, what byte range you access. So every memory access is going to record these things. And then there's sort of a circular buffer, so it won't take up too much memory. And eventually, if you do a lot of memory accesses, like one will fall off the end when you do another one. But the buffer is still pretty big. So this is the information that's going to be recorded every time you read or write from memory. And so based on that, it can say, thread number 1 wrote to this memory, but then soon after, thread number 2 read from the memory. And so there might be a race condition there. So the sort of superpower of the thread sanitizer is it can detect race conditions that haven't actually happened. Because you might think race conditions are so relatively rare, like do I have to catch it in the act while the sanitizer is running? And so the answer is no, because it can say thread 1 did this and thread 2 did this a few milliseconds later. So you didn't actually get a race, but the sanitizer will say there could be one based on the way the order of operations in the code. So that's kind of the superpower, I think, of this tool, is that it can detect race conditions that haven't actually happened yet. Kind of like precognition or something like that, maybe. All right. So this is basically the way it does it. It injects these calls into your code. So every time you read data of a certain size, 1 bit to up to 8, I believe this is bytes. So from a single byte to, since we usually have 64-bit machine words, up to 8-byte access, it will record, you can see the thread, some caller information, the address, and then the length of it. So if you run the thread sanitizer and then you sort of dump out the the assembler level, which I was going to do, but I'll probably skip it, then you'll see a whole bunch of these tsend read, tsend write calls injected inside, inside your code. So this is the way that it's going to work. So again, you can imagine it's very expensive. It really, really slows down your app. Even in my simple example, which you can imagine is just going to have an array and I'm going to access it, it's noticeably slower. And then because of that buffer to keep track of every memory access, it also uses a lot of memory. So again, I forget the exact numbers, but it's like 5 to 10x slowdown and 2 to 5x increase in memory usage, something like that. So let's have a look. We'll just do Swift this time because you had enough C probably. The people, especially the people who work with it every day, have probably had enough. All right. So let's give it a try. Let me just save it once, so I'll get highlighting. .swift. All right. So we'll import foundation. And how are we going to trigger it? I'll take some idea. I, of course, have a way to do it. But what's an easy way to trigger it based on what you've learned about what it needs? Yeah. Sort around to, wow, that's way more complicated. Yes, that would do it. If you had an array and you tried to read from it and then you sorted it on the back, like it's a really big array and you want to sort it in the background because it might take a while. Yeah. Okay. Modify it. All right, I'll go with that. So let's make a number like this. And then let me just start with a read. So we'll get the global queue. I think it's QoS. We'll do the default queue. We'll do it asynchronously. I'm just going to print it out for now. So we'll say Q1 number is like this. So we'll just print it out. And I'll do the same thing. User initiated. I think that's a thing. And we'll do the same thing. I'll just print it out. User interactive, I think, says my notes. I think user initiated is the thing too, isn't it? Anyway, I'll go to user interactive. I'm sorry?
I think it's interaction.
Interact. My notes is really?
Like it's not yellow though.
Oh yeah. Well, this is just Adam doesn't know what it's doing, so that's fine. And then whatever the main thread, quote unquote main thread is, we'll see. We'll run the compiler. We'll see what happens. OK, cool. So I'm going to print it out on one queue, print out another queue, and just print it out. I think this is just like the main queue or whatever. I'm not sure if that exists in command line anyway. There's our app. I think we're good. Let's give it a try. So I'll compile it just like before. Like this. Yes. And I need to give a target. x86-64 Apple Mac OS 10.10.13. There we go. Didn't even look at my notes. See, I practiced. All right. So we got it compiled. Let's give it a try. I'll run it a few times. I don't know what happened here. This is just crazy. I guess the application ended before the queue got a chance to run. So that happens. As you can see, it's totally random. First, sometimes the number is first. Sometimes Q1 is first. This time, the main thread ran through and the queue didn't even get a chance. Q2 is first here. So it's all over the place. It's very thread racy, you could say. But it's just reads, so it's OK. So we think. Let me run it with the sanitizer. And we'll see if that's true. So sanitize equals thread. And then we'll run it. And you'll see how much slower it is. I'm going to run it. And now it's done. So you can see it's a lot slower. I'll run it a few times. Because it's so slow, maybe we won't actually. OK, so it's 2 and 1. Sometimes it's 1 and 2. This one is 2 and 1, and so on. But it didn't actually complain. Because, again, this is just reads. And reads are totally fine. You can read from the thing from multiple threads, and we're OK there. So we're good there. Let's introduce some writes, and then we'll get maybe something more interesting. So on this one, I'll say number is equal to 10. And on this one, we'll say number is equal to 30, something like that. And so we hope this one will print 10. We hope this one will print 30. And then maybe this one will be undefined. I'm not sure. But maybe the number will be set to 10. And then the number will be set to 30. And this one will say it's 30. Who knows what's going to happen, right? So I'll save that. Let's run it. I'm going to compile it without the sanitizer, just so we can see it a few times, like so. All right. So it's 10. This one's 10, 10. Oh, it's 30, 30, 30, 10. So it's always going to be 10 or 30, because 42 will always get overwritten. But again, the order is totally different. It's just non-deterministic, right? So it's no good. Let's run it. No? Oh, here we go. So I'll do sanitize equals thread. And then I'll run it. Actually, let me do -G, I think, as well, to give us debug information. I think that'll make it look a little bit nicer. And we'll run it. All right. So one thing I forgot to mention was the address sanitizer will actually trap the first error it finds. So your program won't run through. The first time it finds access violation, it'll just stop the program. Thread sanitizer will actually continue. So you can see here's my Q2, here's my Q1, and then the actual one maybe is at the top. Yeah, so it's actually here. So it actually lets your program continue to run because it's like, well, it's only a thread violation. Maybe it's not so bad. So anyway, number is 42. So that ran first. It didn't set to 10 or 20. And then you can see there's a closure. Well, it'll tell you there's a write of size 8 at this location. There's a closure that did it. And because I think because I turned debugging symbols on, it tells you the file. Whoops. Force touch. It'll tell you the file and also the line number. So it's pretty handy. If you run this in Xcode, which I don't have prepared, but if you do it with your app and you turn on Thread Sanitizer, you run the app, you'll get this in the console, but you'll also get a nice output in the, you know where you get compile errors? I forget which tab that is, which navigator that is in Xcode. The issues navigator, there's 2 tabs. There'll be one for compile build time issues and runtime issues. And you'll actually get a runtime issue in that, and it looks all nice. And then you can click on it. It'll take you to the code and so on. So it's much nicer in Xcode. But this is sort of the raw output here. So it'll tell you there was a write at this closure. The previous write was at this closure, and so on. So it sort of tells you what's going on. And then this one is thread 2. Or thread T2, it's not really a real number. This one's at thread 1, so it'll tell you what threads are going on. And again, if you're in Xcode, I think it's a little more informative about which thread the problems are. And the thing that we're violating here is our global variable number up here at the top. And then you get some details on the thread. So it's very good. It gives you lots of information. Again, because it is storing the thread ID, timestamps, and whether it was a read and write, and exactly which bytes of memory you're accessing. So it gives you a lot of information to help you debug the problem. So very handy there. And I think that is that one. Why don't we just take a little quick sidebar and say, if you wanted to figure out exactly what it was doing, how would you do it? So you can go look at the C++ source code for the thread sanitizer. Again, there's a compiler component, and then there's a runtime component. So I think it was the thread sanitizer, and I thought, it's injecting this code. It's injecting the tsan read, tsan write in there, but how is it doing it, and exactly what is it doing? So I wanted to kind of trace it down. So let me just look at the help here. So if you run swiftc, you can see there are all these options. You can dump the AST, the abstract syntax tree. There's a famous slide, I don't have it here, but it's like Swift turns into SIL, turns into IR, turns into assembly, turns into this, and it's sort of the whole compiler chain. So I was like, okay, SIL is the next one that's sort of human readable, quote unquote human readable. So I said, let me not compile it all the way, but just compile it to SIL, and I can find the thread sanitizer stuff. So let me just try it and see if that works. So where's my compiler? Here we go. So I'm just going to emit SIL without the sanitizer on, and it looks like this. Okay, so I'll just dump this to a file. Yeah, it's close. Look at all these, look, it's a hash mark, it's comments. Look at all these comments, it's wonderful. All right, so I'll output this just to a file called SIL, just to save it somewhere. And then what I did was I said, I'm gonna turn on the sanitizer, and I'm gonna output it to like, and I could just diff the two and see exactly what it was doing was the idea. So I do SIL, SIL2, and then you say, so it did this instead of this. This is actually the same because this UUID is different. So if you look at the differences, there's not that many, so this is kind of a red herring. It's just this UUID that every time you run the compiler is different. So there's not actually any difference. This is it. So I'm like, all right, it's not at the SIL stage that is injecting the code into my applications. Where what's after SIL? I think it's IR, which is the LLVM intermediate representations. You can also emit IR. So I say, all right, let's try that. So I'll run the thing again. Instead of SIL, I'll emit IR, turn off the sanitizer, output that to IR, and I'll do it with the sanitizer. Is thread, and then I'll diff them, and what do we get? So you can see I get this tsan atomic 128. So this is where I get some differences. If I just look at the file size, you can see IR is 51,000 bytes, and the IR2 is 71,000 bytes. So it's like, okay, somewhere in between the Swift intermediate representation and the IR generation, somewhere in between there is where it's injecting all of the thread sanitizer code. So I don't know, if you're like a compiler nerd, it'll give you sort of hints on where to look. And this is even more human readable, so people will love it. And you can see this representation. You can do a search for tsan, and you'll find various calls to it if you wanted to trace it through. So that was kind of how I went digging to sort of find out where things are happening, and then you can emit assembly too, and it's even more human readable. So, all right, let's wrap up with the slides here. So that's the thread sanitizer. Again, covering our questions of the day: what it is, why you should why you should care, how it works. What is it? Basically, it's a data race detector. You have data access on two threads, and it will help you find out where that is happening, where you have a read and a write that might conflict with each other. Why should you care? Help you find race conditions and other threading issues. Again, threading code that deals with thread is very difficult to write, it can be difficult to understand, difficult to get right. So this is just one more tool in your toolbox to help you out with it. And how does it work? Thread IDs, timestamps, a sort of a circular buffer of every memory access, and that's what it uses to sort of keep track of things. So that's the basics behind the thread sanitizer. I'll just review. Address sanitizer, again, helps you find memory corruption and errors. Maybe not such a big deal with Swift, but with C, Objective-C, I'll call it legacy Objective-C code and be a little unkind. It'll help you find these problems. It can be a security hole and also crashes, so it'll help. I write Objective-C every day too, so I'm making fun of myself. It'll help you find security issues and also just runtime crashes, which are no good. How does it do it? Again, there's a custom injection of code for malloc free and again for memory access. Every time you access memory, it has to check whether you're accessing a poisoned block or not. So where to go from here? You can, again, open the scheme. This is from the Xcode 9 beta 6 or something like that, beta 5, whatever. You can open the scheme, edit the scheme. You can see these things. Runtime sanitization requires recompilation. That's the little subheading there that I was talking about. You can turn these things on. I believe you can only turn on one at a time. You cannot have both address and thread sanitizers running at the same time, I think, because it would just be madness. And again, you can look at the requirements. Some of them only work on Mac. Some of them only work on the simulator. I believe, I'm not sure which ones work on device. I forget now. But you can check out the docs and see. So there's that. You can, there's also the static analyzer, which I didn't talk about, which will help you out with some extra compiler warnings. You saw when we did the stack variable with the size of 10 and we tried to access 15, we actually got a compiler warning. So the static analyzer will help you out with more of those kinds of things. You can check that out. You can look at the Clang documentation, which is slightly less friendly than like Apple documentation, but it has a lot of details on exactly how this stuff works. And there's also Apple documentation, which is much more nicely formatted and usually a little bit friendlier. And so you can check out the thread sanitizer, or the documentation for address, thread, all the different sanitizers. You can check that out on the web as well for more details. I think the address sanitizer, I forgot about thread, but address I think was developed at Google. So they have on some Google website, there's like a wiki and they have more details about exactly how it works. So you can check those out too. I think they're linked from the Clang documentation if you're interested in learning more. That's it. I'm doing more research and doing another version of this talk in a month at another conference. If you have any feedback, questions, things that were unclear or things that you wish were covered, then I will have a second chance to give the talk somewhere else. So I'm doing more research and finding out more things. So if you have any feedback for me, then you can send me a DM or you can look up my email address and send me some feedback, and that would be great. I want to thank the SCORE for hosting us, and I think that's all I got. So thank you. Yes, a question.
So, to go back to the thread sanitizer.
Yes.
So, I guess it's a two-parter. First is, do you know what the heuristic it uses to determine like what kind of writes are dangerous? Like I'm wondering, because if you came across this, you'd solve it. Let's say you throw a mutex around it or something, and you resolve that somehow.
Mhm.
and putting up some sort of access barrier. How does TSAN know that that's there? You know what I mean? Like, how does it know not to warn you in that case? Or is it just, you're always going to get those warnings even if you have proper protection against them?
I believe it uses the timestamps somehow. There's some magical way where it uses the timestamps to detect the time as well. It's not always entirely clear to me,
So it could
but
say,
it's.
like a mutex is released or like or a graph or something. And
There is something in the list of there's I found a list of there's like a switch. There's an enumeration with like all the different errors, and they have a switch that describes each of them. So just based on that, there is one about like accessing outside the mutex. So I think there is some way that it will tell that. I think Thread Sanitizer version 1 was worse, and it was really horrible, and this is now version 2. So I believe it has more things in there. So I don't know the exact details, but I believe it's smart enough to figure that stuff out. It also hooks into some foundation, like Apple has extended it. So like foundation, like dictionary access, that kind of thing, it has special extra code to inject if you're accessing a dictionary or something like that, or accessing an array. So some parts of it are Apple aware. So I think mutexes are also included.
Okay.
Mutexen? What's the plural of mutex? Anyway, that stuff I believe is included and also properly wrapped as well. Yeah.
Is there any industrial strength scanners like 8245 or AppScan in this world?
Industrial strength scanners. I don't personally. I used to use Valgrind back in those days. I don't think that works on the Mac anymore. I think it stopped working I don't remember exactly, but no, I'm not familiar with any of that stuff anymore, though. So. Any other question? Sure. Have you personally found or solved any issues using these tools? Have I personally found or solved any issues? All my thread code is perfect, so of course it's no. No, I haven't. I mean, have I tried it at work? I don't think I've actually tried it at work, so I don't know. But for my own apps, they're usually really simple, so I haven't. But I think as part of the WWDC talk, they talked about how they found a race condition, I think in like Xcode. Like the Xcode team used Xcode to debug Xcode and found either address, like an overflow or a thread race using these tools. So the teams at Apple, I forget, I think it's one of the talks from this year where they describe it. So even the folks at Apple are using it for that, yeah. It still doesn't help the crashes, says Patty, yeah.
So Clang is constantly adding a whole bunch of new sanitizers.
Mhm.
So it's not just the 3 that are available in Xcode. Do you know if those are available in Xcode, or do you have to like download Clang and like compile from? And have you played around with any of those?
No, I think, yeah, like the thread sanitizer has been available for a while, but only recently added to like Xcode version of it. I think part of it is to have support for Swift. They have to add special things to the compiler runtime for Swift specifically. So that was only added, relatively recently. So that's part of it. And then also there just won't be a checkbox in Xcode until they add the UI. So you can go and build it yourself, and it might work. But then the problem is again, it's a compile time thing, but it's also a runtime thing. So you won't have Mac runtime support for some of the sanitizers. So I think you do have to wait for Apple to come around and see it. But you can always keep track with like the Clang LLVM folks and see what's coming down the pipeline and see what's available. Maybe you can like file a radar with Apple and say, hey,
I just did a quick search, and one of the interesting ones that kind of came up right up near the top of the results was leak sanitizer.
Mhm. I think that might be in beta. Like, I think they said, oh, they're working on it or something like that. But yeah, the address sanitizer, I think, actually has beta support for leaks, but it's not 100%. So I think they're going to put it as part of that one. But yeah, it'll be coming. Any other questions? Yeah.
Are there any common, guidelines for when you want to run the sanitizer, or does it matter?
Common guidelines on when to run the sanitizer?
Is it just the last thing before you publish an app, or do you run it regularly? It doesn't
Yeah.
matter at all?
Well, then you'll find the bug. So it's like the second last thing you should do. Probably, I don't know. If I were writing some, I've started writing the network stack and it goes in the background and the callbacks come back, I'd probably just run it then and do a few network requests and see.
Doing a bunch of stuff
Probably, yeah. I would say it's the kind of thing you don't want to do too late, because then you're like, oh my god, I wrote all the network code and now I found out there's this race in it. So I don't know. I would try to set like a mental alarm clock and say, oh, I'm doing a lot of GCD here. Maybe I should try the thread sanitizer, that kind of thing. I'm not quite sure how to put it as part of your workflow. Like, I'm not sure you can automate it because you actually need to run the app and exercise various parts of it. But yeah.
Are there any benefits just having it on your unit test?
having it on, benefits of having it on in your unit test. Yeah, that's a good idea. It is just a compiler flag. I don't know if you could do it in well, if you have unit tests, I'm assuming there's some automated system, like if you're using Jenkins or something to do it. Yeah, you can just set the flag and give it a try. I don't do unit tests either, so I don't actually know. That whole TDD thing, I was just making it up, so yeah. Yeah, that sounds like a good idea, though. You should...
As a official representative, Instagram does not do TDD.
We do have unit tests, but yeah, I don't do TDD personally. Maybe some people do, but we have unit tests. I don't think we enable the sanitizer for the test, though, but that might be a good idea to try. Yeah?
If you're running automation, particularly thread sanitizer, would there be a way to detect that there was an issue? Does that show up? Does that crash? Does that...
Yeah, how would it show up in the report? I know for address sanitizer, it will actually crash the app, so that you'll get a runtime trap, so that would trigger it for sure. Thread sanitizer will just give warnings, so maybe you would need a custom action to like grep the output and look for the word, you know, thread violate, whatever it outputs. Yeah, I don't know, because it does let the app continue. It's not going to stop the app,
Yeah.
so that gets a little tricky. You'd have to actually look at the debug log output. It's not actually going to...
Put that somewhere.
Yeah, that I don't know. I don't set up Jenkins or do any of that stuff, but there's got to be a way to do it. Probably after the fact. After your test finishes, you could, after the fact, look at the logs and look for the word thread whatever and find something. Maybe that would work. Yeah. Yeah.
Race conditions are one threading issue, so what about other threading tools? Other tools are sanitizer.
Yeah, the thread sanitizer does pick up a lot more things than that's just the easy one that I covered because it's easy to demo. Again, you can check out the docs and see exactly what other things it detects. There are things like proper mutex, like if you unlock a mutex and access a variable after. I believe I saw that in the note. Deadlock detection, so it does do other things as well. It's just, I don't know, harder to demo well, it's probably easy to demo a deadlock, but you know, harder to demo. So you should check it out and see. There is a list of things that it'll pick up for you.